Let us consider a case in which there is an impermeable layer between the two zones of interest that have different permeabilities. For simplicity, let's assume that there is no oil present and this reservoir has been subjected to polymer flooding. The question is, how can we calculate the ratio between the penetration distances of the polymer solution in both layers? Each layer will be considered separately. Let's assume that a certain portion of the polymer solution has entered the upper layer. Inside the porous medium, this solution will occupy a volume that can be expressed using the formula for the volume of a cylinder with radius R1 multiplied by the porosity. Why radius? Because we are considering radial flow. This volume divided by the injection time gives the injection flow rate, which can also be described using Darcy's law for radial flow. The same approach can be applied to the lower layer. As a result, we can determine the ratio between the polymer solution's penetration distances in the two layers using these expressions. As can be seen, this ratio depends only on the permeability and porosity of the layers. It does not depend on the viscosity of the injected polymer solution. This analysis shows that in the case where there is an impermeable barrier between the two zones of interest, referred to as the no cross-flow case, increasing the polymer solution's viscosity will not result in equal penetration distances in both layers. An increase in viscosity will not equalize the flow velocities between the layers when an impermeable barrier separates them. In other words, in the no cross-flow case, increasing the polymer viscosity will help eliminate viscous fingering and promote piston-like displacement within each layer separately, as we have already explained in our previous video lessons. However, it will not compensate for the permeability contrast between the layers.